Swayam Prabha. Digital India. Educated India.
I welcome you again for this course on flow through porous media. What we were discussing was that if you have a non-uniform permeability in a stratified porous medium, how do you find out what is the effective permeability? This is part of our general exercise on mass continuity and Darcy's law and application in Cartesian and cylindrical coordinates, and with an objective to find out the pressure equations and velocity profiles. So, what we were discussing in the last class was that if you have two permeabilities that are in series or two permeabilities that are in parallel, how do you theorize them? How do you put them together? So, here you can see that when K1 and K2 they are in series, that means when what we discussed was that if you have a core where here we have up to certain length, the permeability was K1, and beyond that length the permeability is K2. So, now you can see that this length is, let us say, the length over which this permeability is valid is L1, and this length is, let us say, L2, the over which the permeability K2 is valid. So, now what we write here is that L1 plus L2 divided by K effective is L1 by K1 plus L2 by K2. Why are we saying this? One thing you must appreciate here, that whatever flow is taking place, I am injecting a flow, I am having a flow rate Q. So, whatever Q that is going in, that is going through this section L1 section, and then it is further traveling through L2 section. So, you must agree to this, that as long as the porosities are same, so the Darcy velocity, so you can expect the Darcy velocity, or for that matter just simply if you look at the Darcy velocity, that is Q divided by A, and that A remains same, the same cross sectional area. So, essentially you are saying that whatever velocity you have from this side is same as the velocity you have from that side. So, what would be the velocity from this side? It is K1 by mu, and let us say you call this pressure drop across these is delta P1, and pressure drop across this is delta P2. So, K1 by mu 1 delta P1 by L1. Okay. So, that is the velocity that is applicable here. Okay. And you can expect the same velocity to be valid for K2 by mu delta P2 by L2. Okay. I can first of all take out this mu, that is possible, and further I can write this as delta P1 by L1 by K1, that is equal to delta P2 by L2 by K2, and that is equal to delta P1, this is called I think componendo dividendo, delta P1 plus delta P2 divided by L1 by K1 plus L2 by K2, and delta P1 plus delta P2 is basically delta P divided by the sum that we talked about, L1 by K1 plus L2 by K2. So, L1 by K1 plus L2 by K2. So, the velocity through these is basically, the velocity is, we are finding this velocity to be the superficial velocity or Darcy velocity, that is equal to delta P divided by delta velocity is basically K1 by mu delta P1 by L1, okay, and delta P1 by L1 by K, that is equal to this quantity. So, you can write this as K1 by mu and then del K. So, sorry, I should be writing it as not K1 by mu, I should be writing it as 1 by mu delta P1 divided by L1 by K1, right. So, this is what we would be writing, and then I can, let me change it. This delta P1 by L1 by K1 is basically this quantity. So, what do we have here? So, if I take this further, we can write delta V is equal to 1 by mu, and this delta P1 by L1 by K1 is equal to this quantity. So, that means that is equal to 1 by mu delta P divided by L1 by K1 plus L2 by K2. On the other hand, the Darcy velocity, this overall is, we can write, we are looking for that magic permeability which we are calling effective permeability, right. So, this is equal to effective permeability divided by mu into delta P, total pressure drop across the length, divided by L. So, that means I am trying to find out if I call this effective permeability is the equivalent permeability for this entire length L, then the total flow rate has to be equal to the Q by A, that superficial velocity has to be equal to that effective permeability, that means the equivalent permeability for the entire length divided by mu, total pressure drop across this bed L1 section and L2 section combined, and divided by total length L. So, that is how this V is. V is expressed that. So, this magic permeability we are looking at. So, if we are looking at this magic permeability, so automatically I can see this delta P, this is cancelling out here, mu is cancelling out here. So, essentially you get L by L is basically L1 plus L2. So, L1 plus L2, L is basically L1 plus L2. So, L1 plus L2 divided by K effective is equal to L1 by K1 plus L2 by K2. So, this is what you are arriving at. So, this you can generalize. Okay, this you can generalize in the sense, suppose I have multiple sections, not just L1 and L2, I have L3, L4 like this, so several sections. So, you can write this as sum of Li, I running from 1 to n if there are n different permeability sections, divided by the effective permeability is equal to sum of Li by Ki, right. That is exactly what we are talking about. Sum of Li, that is L1 plus L2 divided by K effective is equal to sum of individual Li by Ki. So, L1 by K1 plus L2 by K2 plus L3 by K3. So, I running from 1 to n, n is the number of stages. So, when K1 and K2 are in series, so this is the equation one must consider. Now, if K1 and K2 are in parallel, and mind it, the flow is unidirectional, there is no cross flow, that is ensured, then in that case it is much simpler, in the sense that in that case you have, as I pointed out, that you have this porous bed, out of which one section is having permeability K1 and the other section is having permeability K2. So, now what is essentially what that means is, I am injecting a flow rate Q and that Q is split into two sections, right. So, Q is split into two sections. I will be having some velocity through this section and some other velocity through this section, and they are combined to find the total Q. Okay. So, then what would be the velocity in the, say, let us say at the top one has permeability K1 and bottom one has permeability K2. So, what would be the velocity in this case for the top section? Top section, the velocity would be, now here in this case we can assume that the pressure gradient is same. Okay. So, pressure gradient, pressure P in minus P out is same. So, for all practical purposes, your del P del x, if this is the direction x, if this is the direction x, so del P del x is equal to same for section 1 with permeability K1 and section 2 with permeability K2. So, then in that case you can write here the velocity in the upper part. Now, let us say this particular area is A1. Let us say this particular area is A1. So, this area is A1 and this area is A2. So, then the amount of flow that is taking place from the upper part. So, if you look at the total Q, out of this total Q, on one hand we have from the upper part we have K1 by mu into A1 into del P, let us say del x minus sign, I am putting it, this Q is same as the velocity direction, this Q is not production from a well. So, do not get confused with this same use of same expression, same symbol Q. This Q is the total flow rate in same x direction. So, this is one thing, and then the second thing is minus K2 by mu into A2 into del P del x. Now, see you are following the same pressure gradient here, they are just simple parallel flow. So, in this case now if somebody writes these Q as what? Q has to be written as K effective, as we had done earlier in case of series permeabilities in series. So, K effective into total area A1 plus A2 divided by mu del P del x. So, pressure gradient remains the same with a minus sign. So, now if you equate, you can see here that K effective, because all other terms will cancel out, mu and del P del x, they will simply cancel out. So, you are left with only A1 plus A2 into K effective is equal to A1 into K1 plus A2 into K2, and that is exactly what we see here, that K effective is equal into A1 plus A2 is equal to K1 into A1 plus K2 into A2. So, when this is the situation when K1 and K2 are in parallel. You can extend this by saying that K effective into sum of AI, K effective into sum of AI, that is equal to Ki into AI. I mean, just for the case where it is not just the two layers, but in number of layers. So, I is the ith layer. So, this is the way one can treat permeability variation in a linear system, and if there is a discontinuous variation in radial system, we already discussed this before. Well, now here we have a case which is a continuous permeability variation in radial flow. Now, suppose there is a situation where the permeability variation is not discrete. That means, in a cylindrical system, we said at R is equal to R 0, when R is less than R 0, permeability was K 1, and when R is greater than R 0, permeability is K 2. So, suppose you work with a system where it is not a discrete variation, rather permeability K is changing with radius in a continuous manner. Okay. So, that is why K is written as a function of R. So, in that case, what was our original equation for governing equation for radial flow? What we had that time was that we had for linear system, we had this del square p del x square plus del square p del y square plus del square p del z square, that is equal to 0. So, then when we converted that to radial system, we had said that for radial system, we have 1 by r del r of r k del p del r, k by mu del p del r rather, plus we have similarly, we do not have, instead of x we have r, instead of y we have theta, because we have r theta z system. So, we have some term with del p del theta, but v theta we have ignored for a truly radial flow. So, this that term is not there, and z we said there is no variation in z direction. Okay. So, we had those assumptions there. So, we are working with a 2-dimensional radial flow, and this was the governing equation. What we did last time was we took this k outside, assuming k to be constant. Where we did this? We took k outside, treated k as constant, and we had arrived at that famous equation P is equal to C 1 ln r plus C 2 in our earlier lecture. So, this time this k is not taken outside, rather k is maintained in, k has to be maintained inside because k is a function of r. Okay, k is a continuous function of r. So, then when you do this integration, so k remains inside. So, r into k as a function of r del p del r has to be equal to constant. Okay. So, now this is that time it was del p. That time it was r into del p del r was constant, k was not in the scene, but here now we have r into k del p del r equal to constant, and that constant we can find out is q into mu divided by 2 pi, where q is the rate of flow from reservoir to well per unit sand thickness. So, we are not having, in fact what we can see here is basically this q is what? Q is equal to minus of V r into q is the rate of flow from reservoir to well per unit sand thickness. So, q is equal to minus of V r into 2 pi r h, and h we are assuming to be 1. So, that is basically q. And what is V r? V r is equal to minus of minus k by mu del p del r, that is the V r into 2 pi r h, h is treated as 1. So, then by this logic you can see here that r into k r del p del r, r into k del p del r, that is equal to q divided by q into mu divided by 2 pi. So, this equation will take you to this. So, if you have this equation to be valid, then in that case if you want to go for the pressure profile, so one is to integrate this. So, naturally you would leave this del p del r on the left hand side. So, del p del r on left hand side. So, what you would do in that case is there would be the next step, which is del p del r is equal to q mu divided by 2 pi r into k r. So, this is basically del p del r. So, when you take this integration, when you conduct this integration, so this would be then here you write dr, and you do this integration of del p, you do this integration from pw to p and do this integration from rw to r. So, when you do this integration, you end up with this pr is equal to q mu by 2 pi integration rw to r dr by r kr. So, this is basically this we are just simply write q mu by 2 pi, they have taken it out, and so they are left with dr by r kr plus pw. So, if you do this integration, you end up with this. Now, at this point you have to be provided with this permeability. Okay, so what should be these? What should be the permeability as a function of radius? So, one must provide this permeability. Now, if there is a continuous deposition, let us say one has suspended solids and it is continuously being intercepted by the pore space, by the pore mouth in this porous medium. So, you have a continuously some amount of deposition taking place in the pore space. So, in that case you will find that automatically there would be, because of this deposition, there would be the permeability would be changing. Essentially what you do is, let us say this is a pore, this is a pore. So, the I have, let us say, some particles that are traveling inside. Okay. The pore space is very large, this pore volume is large, but the pore mouth is very constricted. So, when these particles they get accumulated there, so this reduces the permeability. Now, it continues, let us say, as I, so generally as I continue to have a flow, so you will find that there would be a continuous deposition. Okay. In fact, this we will discuss at some point in this course, that because of this deposition will continuously change with cumulative flow or with time. If you have continuous flow, with time you will find more amount of deposition is taking place, and because of this deposition you will find the permeability is changing. Now, permeability generally would be then in that case function of cumulative flow. Okay. How much of such suspended solids are flowing through this porous medium. So, what you would essentially see is that if this is let us say this is the bed, you will find that this part of the pores they have encountered more cumulative flow, more amount of fluid has passed through this at a given time, more amount of fluid has passed through this compared to this side, the downstream side less amount of fluid has passed through at a given time. So, that means there is a less possibility of deposition of such suspended solids. So, you will find that automatically you will be creating a permeability gradient in these. So, permeability would be much more reduced near the inlet section, or but as you proceed you will find permeability is less reduced. Permeability is, and far away you will find permeability is almost same as the initial permeability. So, the permeability this way one can have a continuous variation. So, one must arrive at some kind of dependence of permeability on the distance. So, that once you have that information, you need to feed in that information to this expression for Kr, and once you feed in that expression in for Kr, you can integrate this and you can find out the pressure as a function of R. So, this is the profile when you have a continuous variation, continuous permeability variation, that is what we have been talking about, continuous permeability variation when you have in radial flow. So, this is the master equation. Now, one has to arrive at some kind of permeability expression as a function of distance, and that can be incorporated with the in the flow rate. Of course, you may say that okay, since the permeability is a function of distance, this permeability will be also a function of time, because as more and more particles flowing in, so whether the steady state assumption is valid at that time or not, we have to have some way to work on that. We will discuss this in more detail, but if one considers a pseudo steady state situation, that means at a particular point permeability has already produced some kind of a gradient, a permeability gradient is already being imposed on this porous medium, and at that particular time under pseudo steady state condition, if somebody wants to know the pressure profile, this is the equation to get there. So, now we want to switch gear to something else, and before we complete this exercise, before we complete this lecture, I want to leave a small sort of homework or some small exercise you must take up before we initiate the next lecture. That is, we need to have some good idea of what is a streamline, what is a potential line, and what is stream function and potential function. For that, we need to have you all understand what is a streamline, right? So, what is a streamline? Suppose I have an obstruction here and I have a flow taking place. I have the flow taking place here. So, this flow is, I would see that if I put some paper boats in a river stream and I have a log sitting there which is creating an obstruction, we see that the paper boats will take a detour. Paper boats will go and travel like this. Paper boat will not go and hit there and sit there. Paper boat will take a detour and travel like this. So, one can get a feel for what are the lines the streams are following. Okay. So, in a very layman's term, that is what is streamline, but it has a more rigorous definition that if you draw a tangent to a streamline, that defines the velocity of the fluid at that point. Another definition is that along the streamline, the value of stream function psi is constant. Okay. So, this is having a stream function value of psi 1, this is having a stream function value of psi 2. So, and by the same token, we can find out the potential lines. These would be the potential lines. These would be the potential lines. So, these potential lines are the lines along which the potential function phi is constant. So, these are the concepts of fluid mechanics. So, I would expect that when we start the next lecture, you must you go through these, go do some little bit of homework on this definition of stream functions, potential functions, streamlines and potential lines, because we need to apply them in porous medium. That is the next level of continuity we want to do in porous medium. So, I am closing this particular section, this particular module here. In the next class, I will continue continue our lecture on continuity and pressure profile, but we have to consider now the stream function and potential function. So, just just browse these concepts of stream function, potential function and these streamline potential lines. That is all I have for today. Thank you very much.